Okay, we're going to solve the second order differential equation. Y double prime minus 36y equals 0. So to do this, since these are constant coefficients, 1 and negative 36, we can use the substitution y equals e to the rx. If you're, using a different book than me, or, that r could be a lambda or it could be an m. Different books use different letters for that r. So what we're going to do is, this is our guess. So we're going to plug it into the differential equation. This is our guess as a solution. So we do need to find the second derivative of this to plug it in. So we take y prime equals re to the rx, y double prime equals r squared e to the rx. And now we're ready to plug it in. So instead of y prime, we're plugging in r squared e to the rx minus 36, and then instead of y, we'll be using e to the rx equals 0. And let's go ahead and factor out e to the rx, and we get our characteristic equation, which if you've done this enough times, a lot of people just rush to the characteristic equation, but be careful though. Sometimes this term's a y and a y prime, and you want to be careful on, factoring it out, skipping that step. It's hard to get it wrong if you plug it in every single time, and it's not hard to plug in. So, since this is never 0, the first e to the rx that we factored out, this is never 0. To make this a true statement, we have to set this equal to 0. And let's solve. And we get r equals plus and minus 6. Two solutions. They're unique because there's two of them. So my fundamental set is my first solution. We plug r back in here. That's what we said our solution was. So we get e to the 6x, and my second r, e to the minus 6x, and we know they're both independent, so therefore that is my fundamental set. So to write your solution, your final solution, the general form is c1 e to the 6x plus c2 e to the minus 6x. Okay. Would you like to do another one? Okay, let's do it. So we're going to solve y third derivative minus 6y second derivative plus 9y prime equals 0. And we're going to do the same thing. Y equals e to the rx, and take the derivative. Y prime equals e. Oops, let's put that r in front. R e to the rx, and y double prime equals r squared e to the rx. Plug it into our third order. And the third order, oops, I need one more, don't I? So y triple prime equals r to the third e to the rx. So plugging in for the third derivative, r to the third e to the rx minus 6. My second derivative here, r squared e to the rx plus 9y prime e to the, r e to the rx equals 0. Factor out our e to the rx again. And you get r to the third minus 6r squared minus 6r squared plus 9r equals 0. Yeah, so if you want to look at the difference between this one is just a y, so we ended up with a constant. But this last term here is a y prime, so we didn't end up with a constant. So let's be very careful. That's, it's silly mistake you don't want to make when using, if you just go straight to the characteristic equation. So now we have to solve r to the third minus 6r squared plus 9r equals 0. Factor out an r. Six r plus 9. And we'll factor that real quick. It looks like it's got the same factors. And so we have r equals 0, 3, and 3. So that's our multiplicity of 2. Just writing them both out. We know we have to have independent solutions to be in our fundamental set. So how are we going to take care of that? My fundamental set will include 0, which is e to the 0. It will include x. It will include e to the 3x. And then to make it independent, we could use Abel's formula. But we did that in general. In Abel's formula, in general, we add an x in front. And there we go. We have 3 independent solutions to our third order differential equation. And so to write that as a solution, and e to the 0x, of course, is just 1. We'll just change that to 1. So we get c1 plus c2 e to the 3x plus c3x e to the 3x. Okay, so those are 2 examples of using, for constant coefficients, using the substitution y equals e to the rx. Thank you.